Hey guys, welcome to another dynamics video. Today we're going to be doing a classic banked curve question where a car is driving on a frictionless banked curve, and you can just imagine the car driving into the page and going around in a circle. And we're given that the car is going to be moving at a constant speed, and we're asked at what speed is it going to be driving around the banked curve. So go ahead and try to solve this for yourself and then come back when you've finished. Okay, so this question is kind of confusing because we don't really know where to start, but a good place to always start is just to draw a free body diagram and to see what information we can get from that. So, I have my car. I know that there's going to be weight of the car acting directly downwards, and that there's going to be normal force that acts perpendicular to the plane. And because there's no friction, these are the only two forces that are going to act on the car. Okay, so this car is not going to accelerate upwards or downwards. So we know that the vertical component of the normal force must be equal in magnitude to the weight, because the vertical forces must add up to 0. And we also know that the horizontal component of the normal force, because there are no other forces, must be equal to the centripetal acceleration. So, if we just assume that this angle is theta, and we'll figure out what theta is later, we can write two equations. That the normal force times sine of theta equals mv squared over r, the centripetal acceleration times mass. And also that the normal force times cosine theta is equal to mg, or weight. Okay, great, but we can't really do anything if we don't know what theta is. So let's figure out let's figure out what it equals. So let me just draw the inclined plane, and I have 25 degrees. And let me just draw the normal force, which is perpendicular to the plane. And stemming from the normal force, I'll just draw a vertical line and a horizontal line, which are going to help us find the angles. So, because this horizontal line and the ground are parallel, this angle and this angle are alternate interior angles that have the same magnitude. So, this is 25 degrees as well. And because the normal force is perpendicular to the plane, we know that these two angles add up to 90. So this angle must be 65 degrees. And because the horizontal and the vertical lines are perpendicular, this angle right here must be 25 degrees. And if we look at our diagram, that angle, which is from the vertical and goes to the normal force, is what we just found. So theta is 25 degrees, and it's the same degree as the inclined plane. So from now on, with these banked curve questions, you can just use the degree of the inclined plane for theta. Okay, great. So now we know what theta is, but we still don't know what the normal force is. But because the normal force is in both equations, we can substitute one into the other and then solve for v, which is our only variable left. So let me isolate for the normal force. Equals mg over cosine theta. And let me plug this n into this equation. So, mg sine theta over cosine theta is equal to mv squared over r. Okay, well, we can see that the m's cancel out, so it didn't really matter what the mass of this car was, and all cars are going to have to go at the same speed. So let me isolate for v, and I know that sine theta over cosine theta is just tan theta, so g tan theta, which is just 25 times r, which is just 200, equals v squared. And we can solve for v, and we can get that v equals 30.2 meters divided by seconds. And because it's asking for the speed, we don't need to put direction. And that's our final answer. Okay? I hope that made sense and that you enjoyed the video, and thank you for watching.